Hello guys, welcome to Craftsmart. In today's video we are going to be talking about subspace topology. There's a question here. Let this be a topological space and Y a subset of X. Show that this is a topological space. Show that this subspace topology is a topological space. Now, proof. We want to show that this is a topology on Y, and we know that this is a topological space and Y is a subset of X. Now, for us to show that it is a topology on Y, we must show that it satisfies the three axioms of topology. And number one axiom is that the empty set and the whole set must be in this topology. So, for the first one, we know that since this X is a topological space, then the empty set and the whole set are in this topology. And we also know that A is an open set in this topology, and A here is defined as Y intersects O, and this O is coming from this topology. So for us to form an open set in this topology, we must find an open set from this topology and intersect it with Y to get an open set in this particular topology. So this means that to show that the empty set and the whole set are in this topology, we must first know that that the empty set already is in X, since X is a topology. So this means that the empty set is an open set in X. So we have that Y intersect the empty set, and this will give us what? Empty. And since Y intersect open set gives us empty, this shows that the empty set is in this topology. Okay, and the other one is, we know that the whole space, that is X, is in this topology, meaning that X is open in X, right? So this means that Y intersect the open set X will give us what? Y. And Y, and remember this is in what? This topology, right? So we now say that Y is in this what? Topology. Remember the definition that for anything to be in this topology, it must intersect, an open set from this space must intersect Y, the subspace. Now, we have shown that the empty set and the whole set are in this topology. Next, we want to show that the arbitrary union of open sets in this topology is in this topology. So take any collection of open sets, that is, take a collection of A alpha, so that alpha is in delta, where your A alpha is in this topology for all alpha in what? In delta. Now we know that A alpha is in this topology, so this means that we know that A alpha already is equal to Y intersects O alpha. A alpha is defined as Y intersects O alpha, remember from our topology here. Now we know that A alpha is in this topology, so we want to show the union. We want to show that the union of this A alpha will also be in this topology. So this means that if we take the union of both sides, this will be the union of A alpha as alpha comes from the index set is equal to the union of y-intercept O alpha, as alpha comes from the index. Now we are focused on this part now. Now this part is the same thing as y intersects the union of O alpha, as alpha comes from index. Now this is equal to this. Remember your distributive law. Once you use your distributive law here, once you apply your distributive law rule, you get this. So now we know that, but the union of O alpha, as alpha comes from this, is in this topology since X is a topological space. Okay, since X is a topological space, therefore this means that Y intersects this, because this is in this topology, therefore this is open since X is a topological space. So Y intersect this will also be in what? In this topology. Therefore Y intersects the union of O alpha, alpha comes from index, will be in this topology. Hence the union of what? A alpha, alpha comes from index, is in this what? Topology. We have shown that the arbitrary union is coming from this what? Is in this what? Topology. Now the next thing we want to show is that the finite intersection is also in the what? The topology. Now here we say, okay, take any finite collection of open sets, that is the collection of AI, such that I is equal to 1 to n, where our AI is in this topology. Sorry, I think I made a mistake. So okay, yeah, I didn't make it. Okay, it's right. I thought I didn't put sub y. If I didn't put sub y, it means I'm wrong actually, but since I did that, it means I was actually right. So where AI is in this topology. Now we know that AI is in this topology. We want to show that its finite intersection is in this topology. That is our target. So what we are going to do is that we are going to recall that our AI is equal to Y intersects OI. Okay, for all I equal to 1 to n. Okay, now we're going to take the intersection of both sides, the finite intersection of both sides. Now the finite intersection of AI, where your I ranges from 1 to n, is equal to the intersection of Y intersects OI, where your I equal to 1 to n. Now using your distributive law, this is the same thing as from set theory. This is the same thing as Y intersects the finite intersection of this OI. From your set theory, this is the same thing as this. Now, but recall that since X is a topological space, then this means that since X is a topological space, we know that the finite intersection of this open set is in the topology. That is, if X is a topological space, is a topological space, then the finite intersection of this is in this topology, and we define this topology to be y-intercept, the open set. So this means that this is open in what? X. So since this is open in X, it therefore means that y-intercept, an open set in X, will give us an open set in T of Y. So therefore y-intersects this intersection is in T sub Y. Hence the finite intersection of AI I equal to 1 to n is in T of Y. So we now conclude that Ty is a topology on what? On Y. So that's the end of the proof. I hope you enjoyed the video. Please don't forget to subscribe. God bless you.